Hello and welcome to homework 2 for my separations class. We will be working through part C today, in which I will be explaining and implementing code for calculating bubble pressure, dew pressure, bubble temperature, and dew temperature calculations for isopropanol water in a system using the NRTL activity coefficient model. And so in the second and third part, we're going to generate the constant temperature binary VLE of the isopropanol water at 350 Kelvin. And then we'll also be generating the constant pressure binary VLE at 1 bar. And we will be comparing these plot with figures available online on Google. So without further ado, let's begin and let's get into Colab. So to begin, let's plug in our libraries and values that will let us begin all of this. And so the first is our CHE library, and then like we said before, we were working with isopropanol and water. So let's add this in there. And then we also know that the array is one of 0.3 and 0.7. So we can also grab that, throw this into the beginning of our code. And again, we have completed all of the precautionary measures put into this code to allow us to complete these calculations. So once this runs and is checked green, we'll be able to continue. And like usual, it always takes about a good 10-15 seconds to import these libraries. So we'll be patient with Colab for the moment. All right, double checks, and we are able to continue our code. So let's begin with defining some variables. And the first thing we want to define is our bubble pressure, in which we will be doing NRTL method. And we want functions of composition and temperature. Composition will be noted as X. And then first we want our Y of P, and that's going to be composition times R dot NRTL TL underscore gamma of functions composition and temperature. And we are going to multiply this by R P VAP of function temperature. And then I realized I forgot to put a colon there, so let's back this up. And then next we also need to define our pressure, which is going to be NP dot sum of YP. And then we are going to have to return these values of P and YP divided by P. So let's check on this, see how good we're running. We are good to continue. And in this next part, we're gonna again work with our bubble pressure, and we're gonna put this in terms of Z, which we worked earlier in the problem. And then we're also gonna be plugging in that 300 Kelvin, which was specified in the problem. The next step is gonna be also defining the dew pressure for the NRTL. So we're gonna add another line of code here. We're gonna define dew P NRTL, and for this we're gonna use terms of Y, temperature, a term called niter, which is gonna equal to 100, which we learned in class, and then toll is gonna be equal to 1e to the negative 6. And here we want pvap equal to r dot pvap as a function of temperature. So the next thing we will be calling our g function, and to do this we will be np dot ones like y. And then we need to make a for loop for I in range niter, which we set equal to 100 earlier. We want p old to be equal to 1 divided by np dot sum y divided by g times p vap. We also need x to be equal to y times p old divided by g times p vap. We then need to redefine x as x equaling r dot NRTL gamma as a function of composition and temperature. And then P new, our new pressure, is going to be equal to 1 divided by NP dot sum divided by G times P. And this all needs to be in a parentheses, so it is. And then finally, another if loop. If np.abs p new minus p old divided by p new is less than total, we need a break. And then the last things we need to do is say that x is equal to y. That is correct. And then of course we have to return our values, which we want to return p new, x, and I. So we ran this and we got check marks across the board. And so now we actually need to set our temperature equal to 300. So we're gonna add another line of code. We're gonna say T is equal to 350, I'm sorry, I misspoke, 350 degrees Kelvin. Oh no, just 350. And then we also need to say x1s is equal to lens np dot lens space 0, 1, 101, and y1s is going to be equal to these brackets, and then bubbles ps is equal to these brackets. Now again, we're going to create a new for loop for x1 in x1s. So this is counting as x1s continues. We're going to have a new x1 value for every value of x1s. So we have a lined up terms, and we're going to have p y1s underscore equals bubbles p nrtl np dot array. We're going to have a new parenthesis with a bracket inside, and inside the bracket we're going to have x1 1 minus x1, because obviously if we have the first composition, the second composition will be 1 minus that. And then we have temperature. Next we're going to have bubbles p, sorry, did I do bubbles? This is supposed to be bubble ps. Bubble ps is dot append e. And we also need y1s dot append. These are just pulling from these appendix that we've created. Y1. Let's get out of the for loop. Bubbles ps equals np dot array. All these redefining, I don't know if I'm using it correctly. It's just pulling from the arrays that we continuously are creating to find the values that we want plotted. Y1s. And now we can run this to make sure. We do have an error. Bubbles p, bubbles, where do I have bubbles p? We want bubble. I don't know why I keep saying bubbles. Props. We do have an error here. Let's figure this out. So we were able to find our error. I kept getting a non-defined variable down here, and I thought that we ran good all the way up here, but it turns out that we had a PVAO instead of PVAP, and that issue is cascading all the way down here and giving us these nasty errors. So we were able to fix that, and we can now continue with our code. So now we've completed this section 1 of part C. We've created our calculations for the bubble pressure and dew pressure, and the bubble temperature and dew temperature, and we have set that with a constant temperature of 350 kelvins. And so now we're actually going to move into the portion where we are creating our subplots, and we can analyze them and determine what actually is going on. And so let's add our line of code here, and we're going to do fig equals make underscore subplots. Again, everyone is very familiar with this part as we continue to go on. Big dot add underscore scatter. And again, this is just redefining our variables so we can actually view them on the plot. So the x value is going to have our x1s values, our y is going to have our bubble p s values, and then we'll name this one bubble, or not, bubble. We also have fig dot add underscore scatter x equals y1s. We want y to be the same thing. And our name to be equal to do. And finally, we want to update this layout to make it a little bit easier to understand. Fig.update. This is going to allow us to change the color, the length, the width, and things like that. And so let's set our width to a value of 600, height to a value of 400. And let's see what happens when we run this. We have this fancy looking graph that we are now able to analyze. So when looking at this chart that we created, you can see that our bubble temperature starts here, takes a swift increase, and then flattens out at the top. And our dew, not in inverse, but somewhat of an opposite structure, starts slower, slowly but surely increases to a faster rate. And then once you reach that a certain point, they start to even out, and they follow a similar temperature down the line. So this follows the NRT pattern that we've even looked at in class. And so again, just to reiterate, this bubble temperature rises quickly and falls off. And then this one starts slower, catches up, and then at a certain point, they rise at the same point and follow the same pattern. So now let's continue with part 3 of this homework assignment, where we're going to be generating constant pressure binary VLE at 1 bar. So we're going to be creating a similar graph, looking at the same things, but this time we're going to be looking at the pressure rather than the temperature. And again, this will be 2 lines, but it'll be at a constant pressure this time. So the first one was at a constant temperature, and we were seeing how pressure changes. And this one we're going to have a constant pressure, and we're going to see how the temperature changes. So let's begin. The first thing we're going to want to do is, again, start pretty much just like we did up at the top. We're going to define our bubble T this time, and our TL, and this is going to be X and P. So this is kind of the inverse of what we did last time, and we want T sub 0 to be equal to NP sum of X times RTB of a function pressure. And then we have to define our fruits again, and this will be of T. Make sure you add your colon. And that is not correct, so we're not able to turn that in. And anyway, we just want to return things at this point. So we want to return the NP sum of X times R. Again, that's not right, so we can't use it. And our TL underscore gamma. We need X, T times this value of R times P dot R dot PVAP of T divided by pressure, all that minus 1, because again, we solved for the first composition and now we're just subtracting 1 from that. Nope, not an integer. And then we also need to get out of this definition and set T equal to SP dot optimize dot root scalar. Here we have our fruit, we have x0 equals t0. We want our method this time to be secant, not redo, like usual, dot root. And then here we need to return t x times r dot nrtl underscore gamma. And this needs to be x of composition and temperature, and this will be multiplied by r dot pvap. All right, so let's run this to see if we have any errors. We do. Scalar. Something is wrong with scalar. Explain error. Let's look what's going on here. We have sp.optimize.root scalar, but it should be. Oh, okay. Accept and run. Had a period instead of an underscore, and we are now good to continue. So now, since this is binary, we do need to define the other portion of this, which is going to be dew pressure. And this is going to be functions of y and temperature, so the other half of the composition. And we need to define pvap, that is correct, r.pvap of t. And then instead here we want p equal to 1 divided by np dot sum of y divided by pvap. And then we want to return both of these values, but this instead will be y times p divided by pvap. Again, you can tell we're following the same kind of cookie cutter template, but just plugging in different ingredients to get to a different dessert at the end. It's like cooking. You follow the same fundamentals every time, but you're just adding different things. So let's define our dew temperature, which will be of y and pressure, obviously. I'm going to add our colon, and this time T of 0 is going to be equal to, that is exactly correct. And then we want to define our fruit T, but we don't want to return that value. We want to return dew P of y and t. Perfect. Thank you, Gemini. And the last part, just like we did above, we need to t equals sp dot optimize. That is correct. Let's just double check. X sub 0 method secant. All right, and now we want to return. We do want to return t, but we also need to return y times p divided by r dot pvap of t. So now let's run this to make sure it's okay. I don't know why it's expecting something there. Let's explain this. Oh, yeah, accept and run. I just missed a colon. I thought I was talking about in my return statement. I didn't know what was going on. All right, so now we're able to continue. Bullet. So I did realize that this is going to be the initial guess for part D, so I just took out some text, added it above, so we know where we are headed for the next video. So now we have our final section before we get to actually look at all of these figures and analyze them like we did before. And the first thing we're going to want to do is set our pressure equal to 1e fifth. We also need 1xs is going to be equal to np dot in space 0, 0, 1, whatever 1. y1s is going to be equal to these brackets. And then we need our bubble. I'm going to try not to make as many typos as I did last time. Bubble TS is going to be equal to the same thing. Now again, we're going to create our for loop as we have before, 1 in x1s. I'm sure this looks familiar as it is very similar to what we did last time. as you can see, I'm going to scroll up and show you this after just so you understand how similar it is. But like what we just typed in, if you just take a little scroll up, oh, it's right there. It's super similar. So we're in this portion. Now we need to pull from our appendix that we created, bubble t s dot append t y1s dot append y1. Get out of this for loop. We'll say bubble dot array. And then finally we need to say y1s equal to np dot array y1s. Okay, so now we've created these arrays. Let's double check that we are running correctly. Oh my gosh, I have been append has no attribute append. What? Explain this error. I used append up here, did I not? So why is it giving me issues now? I will unpause once I figured this out and explain to you what went wrong and how we fixed it. That was very, very odd. I think Colab's just being picky. It helped me create this. I had to create a list, or like create a different name, and then append from this list all types of weird stuff. But it's okay. We're now going to go into the plotting section. I don't understand why it did that. I've never ran into that issue before. Fig make underscore subplots rows equal 1 columns equal 2 fig dot add scatter is equals to x equals x1 s y equals bubble ts name equals bubbles row equals 1 column equals 1. Now just to save some time, we are going to copy this and paste it, but we're going to switch this to y because obviously we have a binary system here and we want this name to be do, and here we go. Now let's paste this again just to get the fig.add scatter in correctly. We want this back to ys, but instead y1's going to be equal to, see, I don't like that it did this, y1s underscore list, I think, because it changed my thing. Now we don't need a name for this portion, but at the end we do need to say show legend equals false. And then we will do fig.add underscore scatter. We need to do x equals brackets 0, 1. Y equals brackets 0, 1. Row equals 1. Column equals 2. Mode equals lines. Show legend equals false. Line color, let's do blue. No, let's do red. Let's do green. Let's have some fun. And then the last thing we do is fig.update layout. That's exactly what we want, and we can run. There's gonna be an error, I'm telling you now, because this weird list thing that it had me do. Oh my gosh. Let's see if this worked. Wanted to give an update. So currently this is what our graphs are looking like. These are not at all like the ones that we've gotten in class. So instantly alarm bells are going off. So currently I'm trying to fix this, and I'll update you on what I do to fix this. So after a little bit of tweaking, we were able to fix this. Up in this very first section, I had an issue. I had, I believe, a plus sign instead of a negative sign here. And I just had a couple of syntax errors and a couple different calculation errors that were leading to these funky lines, because I knew it wasn't syntax necessarily, because I was getting a graph, it just didn't look how I wanted. And so now we were able to finally analyze these. So as we can see on this left side, we have our dew line and our bubble line. So at any given temperature, you're able to look at the composition. So here we have 25.25 dew and 0.02 bubble. And as temperature increases, you can see these concentrations. This one slowly is very linear. And then at about, let's say 0.68, they kind of meet and slowly go up together. Whereas this one's more of a steep drop, and then it evens out. And if you scroll up, you can kind of see it's flipped here. This looks very similar to that, it's just mirrored. And then in this one, with a constant temperature, as you increase pressure, this gray line here is linear, whereas this green line, it jumps up and then it slows back down. And so as you can see, it's almost oscillating in between this linear line that it's going to meet back up with. And so if we want to, we can go in here and we want to compare this to available on the internet. So let's search up. So I looked up just NRTL VLE graphs. If you click on this one, if you see this green line, it is almost exactly the same, excuse me, as this green line that we just created. So as you can see, you're able to go in Colab, you're able to create these simulations that will run just like it would hypothetically and theoretically in the real world. So thank you for watching. Again, just as a recap, we went through all of these graphs. We saw how bubble pressure, bubble temperature, dew pressure, and dew temperature are all related with constant temperature and constant pressure, to see how they react with each other. And this has been the conclusion of part C. And in the next video, we will be able to see part D, in which we implement this interactive Rashford-Rice calculation. Thank you for watching.